Okay, welcome back. I'm going to try another one of these Born-Haber cycles, and this time a little less scripted, and I could totally screw up because I haven't tried this one out yet. So that's the idea. I'm trying to get ready for this test coming up really soon here. I want to make sure I've got this down. I'm going to use, well, here we go. Hang on a sec. I'm going to use a new set of elements for this one. I'm going to be working on the Born-Haber cycle again. So let's just take a look. I'm going to take magnesium, okay, and I'm going to take some fluorine. By the way, fluorine I was messed up the spelling on that. That's the way to spell it, right? Okay. That only matters if you have those ridiculous online homework assignments that make you spell things properly for credit. And you know, spelling, I think it's important, but good grief, if I get the concept, leave me alone, right? Okay. So anyway, here we go. I've got a new equation to put together, and this is what I want to find out the lattice energy for. Okay, this is it. This is magnesium. You know what? I was going to write it up here, but that's not going to be particularly useful. I'm going to come down here and write it right where it starts, so I don't have to do everything twice. I'm getting a little more efficient, I hope. So we're going to start out with this equation: magnesium in its solid state, okay, plus fluorine in its gaseous state is going to yield magnesium fluoride. Woo, all right. All right. Now that's going to involve a certain amount of looking for the change of energy in this reaction. I thought we were looking at lattice energy. The lattice energy is given in this one. So really what I'm trying to find out in this question is the delta E for the reaction. So this is my starting point, okay? I'm going to have all these other steps, like, you know, turning it into a gas, stripping electrons, and so forth, and eventually we're going to come down here to this, okay? How much energy is there between here and here? What's the balance? And, you know, these charts, they sort of help going through this cycle, but for me, as a spreadsheet, it's so much cooler. All right, here we go. I've got, well, how do we want to do it? First of all, I'm going to take this magnesium solid, and I need to sublimate it because we're always going to work with a gas, right? So here we go. Magnesium solid to a magnesium gas is going to require, looking at my notes here, magnesium sublimation is going to be 150 kilojoules per mole. Okay, and the equation is given in moles, so right, just molar quantities. If we were dealing with grams, we'd have to do a conversion. Nothing that nasty here. 150 kilojoules. Now it's positive because we're putting in energy to the system to go from solid to gas. That makes sense, right? Okay, next step, we're going to let's see. Next step, we're going to go from sublimation. We're going to ionize the magnesium, right? So this magnesium, as we saw up above, same as the last example, it's in two ways, so that means it's got two electrons it can give up. The first electron that it gives up, magnesium, and I'm going to leave off the states for now just because now we know we're in a gas. To get to here, plus this, is going to be first ionization, that's 735 kilojoules per mole. Okay. The second one, as you might guess, is going to take a little bit more energy, right? Because the protons are hanging on tighter to the electrons it's got left. The pain of the loss, I guess. I don't know what you call it. Okay, so this plus 2E, and that's going to be my second ionization energy for magnesium, and that's 1444. Maybe, you know, magnesium looks at electrons like it's kids, and that's why it's, no, has nothing to do with that. Okay, I ramble, you'll notice. The next step is, let's see, we've done, we need to separate those fluorines, right? The bond energy of fluorine molecule. Okay, so bond energy. You know what? No, there's an easier way to write this. Okay, I'm when I say the bond energy of fluorine, I'm going to take this F2, okay, and I'm going to separate it into 2Fe. And to break them apart, because they're pretty happy. That was really sloppy. I don't know what I just did there. Can't talk and write at the same time, I guess. 2F, that's what I meant to say. I don't know where that E came from. Okay, so this is the bond energy, and that's going to cost 154 kilojoules per mole. So far, so good, right? Except for now I need a line. Tell you what, I should have done this. I left out a step, and you saw that in the last video too, but I didn't fix the chart because I'm lazy. All right, so first time, where were we? Oh yes, so we separated those two. I got the bond energy, sublimation, second ionization, first ionization. You know what? Actually, that was silly. I didn't need to do that. Okay, so let's just do a little reality check here. I went from solid to gas, from gas to ionized magnesium gas. I went from fluorine to two individual fluorines from the diatomic molecule. And now that they're separate, they're ready to take on some electrons. And so that's what I'm going to do. I'm going to say, this is the electron affinity. Okay, so the electron affinity is we're going to take these two electrons here and we're going to put them here, because now that the fluorine's all by itself, not sharing with the other fluorine, they'll be ready to take things on. So that electron affinity is going to be a negative 328 kilojoules per mole. And like I said in the last video, think of the fluorine saying, "Oh, look, all day long he's there, I wish I were neon because neon's so cool," right? And it finally picks up another electron and he says in his mind, "I am neon." Ha! Sighs and heat goes out. Okay, that happens twice because we have two fluorines. That's good, right? Okay, so we go the electron affinity and all those things add up well, hang on, we can't do that yet. The last thing we need to know is the lattice energy. Okay, and that's, you know, getting us from all these steps down to the final place we wanted to be, which was magnesium fluoride. That's not magnesium. There we go. And I guess if I wanted to be strictly accurate, I shouldn't do this up here. Okay, and because that's the number we're looking for, and we'll find all that out in just a minute. Is that right? Is that right? Oh goodness. This is slightly different than the last one I did. This is what happens when you work on the fly. Okay, it doesn't matter. We're going to get there. So I said the lattice energy was negative 2913. That's a 9. 13 kilojoules per mole. Okay, so that's that. Sorry for the bad handwriting. It's really the lag, I promise. Okay, so now we're just going to add it all up, right? What do you think about this? Okay, well, we know all the pluses, we know all the minuses. I'm just going to take a gamble at looking really foolish. If not, I'll figure it out, and you'll see my mistake and hopefully not make the same one. Here's what we're going to do. I'm going to take my handy-dandy Hewlett-Packard calculator. I would, you know, I could turn on the webcam and show you the real one, but it looked just like this. Okay. So here we go. It is, we're going to say 150. Okay, so 150 for sublimation. Right? The next two are going to be 735. That kicks off the first electron, 1444. Kicks off the next electron. Bond energy, that's right here, right, is going to be 154 because we're breaking up that diatomic fluorine. And then, oh yeah, electron affinity, so we're going to have 328. And that happens twice, right? So I'm going to say 2 times negative 756. And the last thing is 2913. 2913. negative, right? Because this reaction of forming that salt kicks off a lot of energy. Okay, and now I'm going to just total the whole thing up. Plus, 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 plus. Oops, too many. Okay, anyway, 1386. I'm really nervous now because if I'm thinking about it, you know, I'm saying, okay, all this is where we started. Well, I want to say that goes right here, right? Because, oh, maybe I took these. And, well, let me check something real quick. Oh man. You know, I went into this thinking that the answer would be on the next slide. Let's see if it is. 14. Da, 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 energy of sublimation. Na na na. Okay, I'm going to pause for a minute because you don't want to watch me think this out. Hang on. Ha! Okay, I'm back, but you didn't know that I was gone that long, right? Thanks for waiting for as long as you did. Okay, you're 10 minutes into this and you really want to get done. Here's where I kind of screwed up. I was on the right path, but you know, on the previous example, I didn't know the lattice energy and it was okay to add everything up. And here's what we're going to do this time. So I've got this, and I've got this, these two sides. That's what I'm going to total up separately, okay? And that should get us the answer I was expecting. Although I should qualify that because science should not be about getting the answers you're expecting, right? But you should try to get the right answers. That's important. All right, so here we go. This is, let's start from the scratch again, I guess. We've got 150 here. Okay, that's sublimation again. Let's do 735. 735. And we're going to do 1444. And 1444, and then 154. And I'm going to stop right there. I'm going to add up the left side first. Okay, so here's my left side. Dun, dun. Okay, so 2483. Good grief. Okay, 2483. Right, slowly. There we go. Okay, kilojoules plus. Now I'm going to look at this other side over here. And that's going to put me at 328, 328 negative, 2 times. Okay, and that's electron affinity. And the next part is going to be 2913. And I'm going to add these two left side ones together. Right. Okay. That looks better. Okay. Now I'm going to subtract, or I'm going to add, if you want to say, 3569. Oh, that was sloppy. Hang on a sec. 3569. That's what I want. Okay. Equals, well, that's easy, negative 1086 kilojoules per mole. I'm running out of space over here. Okay. That is the number I was looking for right here. Okay. So let's change colors. Okay. So the change in energy for this reaction, the total change in energy is going to be, well, let's see, looking at significant digits, there's 3, 1, 2, 3. That's going to be 109. Excuse me, 1,090 kilojoules per mole. And I hope that helped you out. That helped me out. All right, talk to you later. Bye.